You've heard it a million times. Supporters of wind, solar, and other renewable energy technologies argue that they're more environmentally friendly than fossil fuels, nuclear, and hydro. Energy expert Mark Mills, author of Mines, Minerals, and Green Energy, a reality check, joins us in our live stream tonight to explain why the truth is exactly the opposite. Please invite your friends to join us. Stay with us. This is going to be a lot of fun. Good evening and welcome to From the Stacks. Glad to have you back with us tonight, or for the first time if you're new to us. We are speaking for the Cornwall Alliance for the Stewardship of Creation. This is a small nonprofit organization that I lead. We are a network of just under 70 scholars. About a third are natural scientists, including some of the world's top climate scientists, by the way. About a third are economists, usually with a specialization in either environmental or developmental economics. And about a third are philosophers, theologians, ethicists, religious leaders. And we work to educate the public and policymakers on biblical earth stewardship and economic development for the very poor around the world, and the gospel of Jesus Christ, all intertwined. And tonight we're going to be talking about claims that wind and solar and other renewables are more environmentally friendly sources of energy than fossil fuels, particularly. And we have a wonderful guest with us tonight to discuss that. I'll introduce him in just a minute. I also would like to just let you know that through the month of April, we are going to be featuring a booklet by this guest, Mark Mills, called Mines, Minerals, and Green Energy, a reality check. And for this month, as our way of saying thanks when you give a 100% tax-deductible donation of literally any size, we would be glad to send a free copy of this to you. To request your own copy, simply go to cornwallalliance.org, click on the donate button, and when you come on page 2 of the donation form to the comments field, put in promo code 21-04 and just write in mines, minerals, and green energy, or even just mines will be enough. We'll know what you're asking for, and we will be delighted to send you a copy of this really stunning report, which will be the main topic of our conversation this evening with its author, Mark Mills. Mark, thanks very much for joining us this evening. Glad to have you with us. I'm not hearing you, Mark.
It's my pleasure. Thanks for inviting me. My audio is live. I'm good. I'm ready for the internets.
All right. Well, something happened, I guess, on the platform there, but it's going fine now. I want all of you to get a little bit of an introduction to Mark. I'm going to say a little bit more about him than I usually do about our guests, because I just find him to be a fascinating man. He is a senior fellow at the Manhattan Institute and a faculty fellow at Northwestern University's McCormick School of Engineering and Applied Science, where he co-directs an Institute on Manufacturing Science and Innovation. He's also a strategic partner with Cottonwood Venture Partners, an energy tech venture fund. And previously, he co-founded Digital Power Capital, a boutique venture fund, and was chairman and CTO of ICX Technologies, helping it to take it public back in 2007. He's a regular contributor to Forbes.com and is the author of Digital Cathedrals in 2020 and of Work in the Age of Robots in 2018. He's also the author of The Bottomless Well, The Twilight of Fuel, The Virtue of Waste, and Why We Will Never Run Out of Energy. I'll be asking him just a bit about that in a few minutes. His articles have appeared in the Wall Street Journal, USA Today, and Real Clear Politics. He's appeared as a guest on CNN, Fox, NBC, PBS, and The Daily Show with Jon Stewart. And in 2016, he was named Energy Writer of the Year by the American Energy Society. He's testified before Congress and briefed numerous state public service commissions and legislators. He served in the White House Science Office under President Ronald Reagan and subsequently provided science and technology policy counsel to numerous private sector firms, the Department of Energy, and the U.S. research laboratories. Early in his career, he was an experimental physicist and a developmental engineer at Bell Northern Research, which is Canada's Bell Labs, and at the RCA David Sarnoff Research Center on Microprocessors, Fiber Optics, and Missile Guidance, earning a number of different patents for his work. He holds a degree in physics from Queen's University in Ontario, Canada. Mark, it is truly delightful to have you here. You are that sort of polymath person who can bring in insights from all kinds of different fields in any discussion. That I'm sure is going to make this fun. In short, Mark is smarter than your average bear, a whole lot smarter than I am, I'm sure, on all things related to energy. So welcome here, Mark.
Thanks for that overly generous and overly long introduction. I appreciate it. Thank you.
Well, I did want to just get back to the book, The Bottomless Well, and I'll say the whole title again because it's wonderful. The Twilight of Fuel. Maybe you can explain each one of these parts of this title for us. The Twilight of Fuel, The Virtue of Waste, and Why We Will Never Run Out of Energy, which you co-authored with Peter Huber. I read this a little over a decade ago, and it's been one of my favorite books on energy physics, energy engineering, energy economics, energy policy ever since then. And it's just an amazing book. Would you just describe for us the overall thrust and how's it been received out in the public and particularly in the community of people who are very much into all things energy?
Well, when the book was published, it was satisfying to see it go to #1 in Amazon Science, which is, an accomplishment. It's not a popular book in the sense of, a novel or a political expose. As you point out, it's really a science book written for non-scientists who are interested in the science of energy and the engineering of energy. When Peter and I wrote it, we asked ourselves a question in advance. You sit down with a co-author. Co-authoring is hard. Peter's one of the very few people I've ever genuinely co-authored anything with. By that I mean we iterate back and forth, overwriting each other's prose. Do the same with one of my sons now, as it turns out, who is a PhD in philosophy of science. I love writing with him, comparable to my writing with Peter. But we wanted to, in doing that book, our question was, do we want to write something that would stand the test of time, or that would be reactive to the politics of the day we were writing the book, which was, as you point out, more than a decade ago. At the time the book came out, it was at the peak nonsense about peak oil supply, 2005 and 6. And hence the title, The Bottomless Well, because we're about energy, and the energy du jour then and now is always about oil. But then we were running out of it. And we were told, which was nonsense. So the subtitle, The Twilight of Fuel, is an acknowledgement of the direction of history, which is a good thing, and which we hope will continue and should continue, which is that the awareness of and the cost, the share of society's money and resources devoted to getting energy, food and fuel, shrinks
Uh,
into the twilight, disappears into the background. For almost all of human history, getting food and fuel consumed 80 to 90% of any economy's GDP, and most of the time, and not just the efforts of societies throughout history. We spend about 10% of our GDP on food and fuel now. And we should spend 5% and we should spend 1%. It should recede into the twilight. That's a marvelous thing because it frees up time and money for other pursuits, for protecting the environment, for protecting other people, for education, for entertainment. So the twilight of fuel encompasses that entire critical trajectory, the arrow of history, if you like. The virtue of waste is a nod to thermodynamics in the direction of engineering. Put this way, there's a profound difference in energy between the photons from burning a log and the photons from a laser. But they're both photons. They're both measured the same way. We use the same units to measure them. The only difference between the photons from a fireplace is that the photons in the laser are highly ordered. You basically, they're anti-entropic. We strip entropy out of them. We can weld metal with lasers, communicate on a laser beam's photons. We can fix an eye and weld a retina with a laser. The photons from a laser have magical properties that the photons from a fireplace don't. But to get from the photons in a fireplace, that kind of energy, to a laser's energy, we have to go through a whole set of engineering conversion steps, a whole set of processes along the way. Every one of those steps in the universe we live in results in an inefficiency, waste. But every one of those steps adds value, economic value, but more importantly, technology and social value to the energy. So the step along each way from turning raw minerals and raw energy into ordered crystals that allow you to make ordered photons is profoundly inefficient, but profoundly economically valuable. Therefore, the virtue of waste. And finally, why we'll never run out of energy is because, for all practical purposes, the universe is only made up of energy. It's essentially infinite in supply. We didn't create energy. We were created somehow, but energy, we didn't create it. We didn't create the sun, the wind, the flowing waters, oil or gas. These are marvelous resources that exist in nature around us. And what we invent are the machines to access the unlimited supplies of energy in ways that are economically acceptable, environmentally acceptable, and useful to society. But there's no limit to the supply of energy. This whole notion that's been anchored in the Malthusian thinking about energy since Malthus, accelerated in modern times in the 1973 oil crisis, 79 oil crisis, is fundamentally intellectually bankrupt and just wrong. So that's a long, you can see why we just wanted a few words to capture all those things in the subtitle. But that's, as you know, what the book's about. Those features of energy, how we coax out of nature using the physics we understand, using the engineering that we have available, all these incredible tools from lasers and light emitting diodes to steam engines to combustion engines to electric motors and batteries and X-rays. These are all energy phenomenologies that are only created starting with minerals in the earth. Everything starts with minerals in the earth, with the atoms that exist in the universe that are infinitely recycled, ironically. Once they're created, we very rarely have an ability to destroy them. By that I mean, as you know, in physics, you can actually destroy matter and make energy, but it's extremely rare, very small quantities. And that's how everything is created. But to create stuff, to make the built environment we live in, to operate and move things, you have to convert energy from one form to another. It always entails an efficiency loss, which is, quote, waste. Waste is a misnomer.
Yeah, I particularly wanted you to explain this business about the virtue of waste. I mean, most everybody grew up hearing, waste not, want not. But in your discussion of how we refine energy from the very diverse, very diffuse condition in which we find it out there in the world to the kind of extremely refined, extremely concentrated form that is actually useful to us as electricity or as transport fuel and so on. You talk about how that is a process of almost constant waste, but it's virtuous waste. Just explain that a little bit, because I found that just fascinating as I read the book.
It, again, it was a word chosen to reduce a longer thought, and the longer thought is that all of history, humanity has had the pursuit of technology and the use of energy. And if I back up a step, everything about our universe comprises three things. It comprises the atoms, the materials that exist that we have access to do something with, information about them, and energy that's used to change their form. That's what everything is. Everything that we build is taking materials with an idea and a knowledge of how the materials can be assembled and use energy to do that, to do something. And the something falls into just two buckets for all of history. One bucket is survival. By that, I mean creating food and shelter, the ability just to exist and to survive nature's predations. Nature has been trying to kill man since man existed. Nature is very hard on man. We use energy, materials, and our knowledge to survive. But as we use less and less of our energy and materials and knowledge to just survive, we do other things. We create comforts and convenience and beauty and harmony. I don't mean by harmony, I don't mean people hugging and getting along. I mean harmonious things. So the long arc of history has been to figure out how do we fight entropy, and fighting entropy, which is disorder, the virtue in using energy and therefore wasting it because of the conversion processes, is to achieve
Yeah.
longevity, comfort, convenience, and beauty in the world. Those things all cost energy. They all require fighting entropy. Fighting entropy requires using energy. So, yes, there's waste in the simplistic sense. It's stupid to waste things. The problem is that we've conflated energy inefficiencies with the word waste. That began back in the early 70s, and it's a terrible conflation because markets and people generally don't like to waste things. People aren't typically wasteful because waste costs money. True waste is expensive in economic, social, and environmental terms. But energy waste is not an expense. It is a price you pay to pursue beauty and harmony and order.
Yeah. Well, I think it'd be a lot of fun to spend an entire program just talking about that book, but that's not our topic tonight. The topic tonight is your paper, Mines, Minerals, and Green Energy: A Reality Check. You did that for the Manhattan Institute. Before we get into that itself, just tell us a little bit about the Manhattan Institute and your role in it as a senior fellow.
Well, the Manhattan Institute is, as you know, probably all of your audience knows, is one of the right of center, as they say, think tanks. Think tanks were created when they were created some decades ago as quasi academic organizations, places of scholarship, where the scholars, the fellows, job is education, uh, directed at policy typically, because understanding how we run governments, politics matter, policies matter, and one hopes that they're anchored in reason. So there are reasonable disagreements politically, left and right, as it were, but we should at least begin from the basis of facts. So that's what think tanks are supposed to be about. Manhattan Institute is based in Manhattan. I live in the Washington, D.C. area, and I,
Mhm.
I occupy a corner of that university, the MI, as the scholar in residence is where in energy and technology matters. I do a lot of my work in robotics and communications. My next book is only a little bit about energy and a lot about technology, robotics, artificial intelligence, and the coming age of the cloud. But there's an energy component to that because there's an energy component to everything. So that's MI. They've been a very good home to me as an anchor to write things and testify before the Congress and Senate on on matters of public policy that I think affect our common future.
Yeah. Good. Well, prior to writing Mines, Minerals, and Green Energy, you also wrote another study called The New Energy Economy, an exercise in magical thinking. Uh,
Yes.
in, in that, you pointed out that many enthusiasts for green energy, as you put it, believe things that are not possible when it comes to the physics of fueling society. One of those
Yeah.
beliefs, you said, is that clean tech energy can echo the velocity of the progress of digital technologies. Now, that's an
Right.
important claim to challenge because lots of green energy advocates respond to criticism that green energy is more expensive and less reliable than fossil fuels or nuclear or hydro by saying, hey, it's just a matter of time because improvement here can mirror that of the digital world. Well,
Right.
what was that trajectory and why are they wrong?
Yeah. I mean, that's the reason that the title "Magical Thinking." We can disagree about uh, goals, and we can disagree about uh, you know policies, but it's sort of annoying to have to agree to disagree about physics. So the nomenclature is the problem. We have this clean tech nomenclature, and solar panels made out of silicon, computers made out of silicon. Your smartphone has silicon in it and lithium batteries. Electric cars have lithium batteries and a lot of silicon, and so it seems like tech. And we see a lot of analysts, to your point, explicitly claiming that we are on a trajectory of an exponential overuse of the word exponential. Apparently, they don't know what an exponent really is, but it's all right. An exponential rate of change in energy, a transition that's accelerating. And for the naysayers, just take a look at what happened with the landlines to cell phones and the internet and computing. And well, okay, the physics of energy and the physics of information are profoundly different. They're both domains of physics, but let me analogize it this way, because energy doesn't scale the way information scales. They, in fact, scale in the opposite direction. We can pack more and more information into smaller and smaller spaces because information is fundamentally a mathematical concept. We're trying to represent a 0 or a 1 and represent it by switching a transistor. So we make the transistor smaller and smaller. We don't care how small the transistor is. The 0 is always a 0. The 1's always a 1. So if you can keep making them smaller and switch them faster, you speed up information. And that process has always been an energy process. When I worked in microprocessors decades ago, in the early days of large-scale integration, it was obvious that our goal to switch faster, to make computers faster, you had to shrink the transistors. Because if you shrink them, you want to use less energy, less time per switch, and you still had an on or an off, which is the digital realm. That's what digital computers are about. So the result of that is you kept shrinking transistors, is that we ended up with an energy efficiency gain. It was astonishing. Basically, a billion-fold increase in the number of logic operations you can perform per unit of energy over the last 40 years. That's astonishing. You can do those things in information. You can't do those things in energy with machines and people and tons and heating and buildings and moving airplanes. If you could, to illustrate how silly that would be if it could be done, if there were computer-like gains in energy machines equal to what computers actually did, that would mean that soon we would have a solar cell that would shrink to the size of a postage stamp, and that one solar cell would power a building the size of the Empire State Building forever. That'll never happen. It's impossible. The physics are impossible. There's not enough photons arriving on a postage stamp, even if it operated perfectly. It'll never happen in the universe we're in. Or I'll give you a battery example, because the batteries are so popular these days in electric cars. If clean tech batteries followed the trajectory of computing, of odd people, then in a few years, a decade or so, we would have batteries the size of a paperback book or a cigar box, depending on your proclivities, that would have enough energy to fly an A380 from New York to Tokyo nonstop. That will never happen in the universe we live in. There's nothing in the lithiated chemistry that makes that possible. It's physically impossible. It's not maybe we wait longer, maybe we spend more money. It can't happen. It happens in comic books. It can't happen with the physics and the chemistry of batteries. Even if the batteries were perfect, even if all the energy in the lithiated chemistry could be perfectly used, which it can never be perfectly used, batteries will never match oil. In fact, this is the starting point to be specific about chemistry, the physics of the molecules. The energy contained in the lithium molecules, the goo, is known. The maximum amount of energy that exists in those atoms and molecules is a known number. The energy contained in hydrocarbon molecules is also known. There is not just 50% more or 500% more, there is 5,000% more energy in a pound of oil than a pound of lithiated chemicals. It's a huge gap that will never be closed by spending money or aspirational policies. Does it mean that batteries aren't useful, electric cars aren't useful? Of course they are. And they have extraordinary utility. If it weren't for the lithium battery, the smartphone revolution would never have happened. Your phone would weigh a pound. It wouldn't weigh ounces because lead acid or nickel cadmium battery would be just too heavy. So these are important technologies. They've excited people, but their excitement has got them into magical thinking.
Why, Daddy? How come?
Why?
Can't we just have it the way we wished? you know, I, I look at our society around us, and all too often I think that's sort of the way it goes. It's we wish, therefore it will be, and that just
It's not an unreasonable. So I have sympathy for that sentiment. Think about it this way. So when someone says, and this is how every politician, ever since 1969, we've invoked the moonshot to solve any problem. Everything's called a
Mhm.
moonshot. Moonshot to cure cancer. Moonshot to cut carbon emissions. Moonshot for this. Fair enough. The idea of going to another planetary object, the idea of going to the moon, has been around for hundreds and hundreds of years. In fact, arguably 1,000 years, but certainly hundreds of years. And it was an astonishing accomplishment, which we sort of wished into being, right? I mean, but here, there's a twofold problem with using that sort of thinking that, well, we spent enough money, billions of dollars, and we just said, we'll do it, and we did it. Is first, the moonshot was made possible because of physics and engineering that we knew would work to do that had been invented before Kennedy gave his 1961 speech. I think it was 61 at Rice University. So that he didn't give that speech out of the blue, so to speak, thinking it was impossible. Engineers had already told him that the reliability of rocket launches were on the asymptote. We had a 90% chance of not killing people on the launch pad now. They knew it was dangerous, and it was more dangerous than it is now, even though it's still dangerous. We had rocket motors in Venturi. We had the guidance system. We had communications. We had all the tools. It was a stretch. It was going to be hard, but the tools existed, so we could wish it into being. A lot of the things that people are talking about in the energy world today, the tools don't exist. There's no physics for it. They don't exist. The other part of the failure on the moonshot analogy, or the other one that's often used, is the Manhattan program. We'll have a Manhattan Project do that. They're both the same in this sense. Getting to the moon, putting a dozen people on the moon a half dozen times, amazing. Solving the, quote, energy problem is like putting all of humanity on the moon forever. These are profoundly different problems at profoundly different scales. And the conflation between the two is embarrassing and silly. There's lots of moonshot things we can do to solve very specific, narrow objectives that may not be scalable to society, maybe just too expensive, maybe impossible, but they're not moonshots. A Mars shot's a Mars shot. Fixing a single, coming up with a different kind of aircraft you could call a moonshot. I'd like to have an airplane that uses 40% less fuel. Doable, you know. I'd like to have an airplane that uses no fuel. Not doable.
Yeah, great. Now, I want us now to dive into mines, minerals, and green energy. And I want to start off in a sort of a strange way, not referring to a specific thing in it, but rather I want you to sort of say for us what would be the chief things that should be learned about energy in education in grades 1 through 4, in grades 5 through 8, 9 through 12, and then undergraduate? No graduate stuff here, but so that American citizens come out with enough basic understanding of the physics, the engineering, the economics, maybe a little bit of the policy of energy, to be able to exercise their citizenship, their desire to influence policymakers, to influence their elected representatives in a well-informed way. Can you do that for us? I'm sure it's a big challenge.
Well, most of what you need to know, you could probably apply the educational level of grades 1 through 4, since most of most of the scale things I've talked about are arithmetic, and you learn arithmetic pretty early. Kids get pretty good at it pretty fast, and most of the basic principles uh, are obvious to kids in elementary school. Well, let me put it in sort of maybe three buckets of things that are knowable, and then obviously, as one learns more about society and the complexities of making the world operate, laws of unintended consequences, the real world's a little different than the theoretical world. But begins with uh, there's no such thing as renewable energy. Let's just do that for a start.
Okay.
Um, the the energy sources that exist in the world of all kinds, wind, sun, moving water, moving tides, oil, gas, coal, exist in quantities that, for all practical purposes, are infinite. That is, we're not going to run out of them in timeframes that have any meaning for hundreds, centuries and centuries. The fact that wind flows and oil is trapped below the earth is the detail. In engineering, it doesn't change the quantities. The fact that wind is, quote, renewable is irrelevant. Every energy machine is built from materials in the earth. All machines wear out. Therefore, no machine is renewable. Everything wears out. That's entropy. So the key thing on an energy is always, and this is the sort of the grade school reality, since once you know that these, and you state the obvious, it's obvious when you state it, all machines have to be built to extract energy from nature. Energy in nature is free. We didn't put it there. You have to pay for land to get to it. You have to pay for machines to access it. You have to pay for machines to convert it. True for all energy sources, which means all machines wear out. So what you have to know is how much machinery do I have to build to get a unit of energy, to go a mile, to heat a house for an hour, to illuminate a room for an hour. It's the quantity of machinery, and therefore the quantity of materials to make that machine, that determines the cost of the energy, determines the cost in economic terms and in environmental terms, because quantities of materials you extract from the earth have an environmental cost, and in social terms, because the quantities that you extract and where they're extracted from have social implications. So until you start with understanding that there's no magic in this, it's always about materials extracted from the earth, converted using other machines, and the machines that wear out that have to be maintained and replaced, then you begin to understand where the real costs lie and why solar and wind are so difficult to replace hydrocarbons, because the quantity of materials you need to produce a unit of energy service, going a mile, heating a room, heating up a billet of steel, whatever it is, heating up a billet of silicon, the quantity of primary materials you need to make the machinery along the way is 10 times higher going the solar and wind and hydro route than it is with hydrocarbons, with oil, gas, and coal. Reason for that, and this is, kids learn this, I think, in 5th or 6th grade, is that wind is powerful when it's a hurricane, but other than that, it's not that powerful. If there were hurricane winds on the surface of the earth all the time, there'd be no civilization. So wind is diffuse. Sunlight's diffuse. If sunlight were too intense, our planet would be like the planet Venus or Mercury and be uninhabitable. So we have diffuse energy sources that require lots of hardware. The hardware requires extraction of materials, more than people realize, because you don't see them. They're remote. They're not in our daily life. So the other thing you could do, and most kids learn this by sixth grade, is use the magic Google machine to Google up questions about how much copper is in a car. You know, the copper industry is happy to tell you there's 4 times more copper in an electric car than in an internal combustion engine car. So does that matter? Well, there's lots of copper in the world, but it means you're going to mine a lot more copper to make cars if they're electric than if they're internal combustion engine. You won't be extracting as much oil and gas and coal. You'll still be extracting some, because to mine the copper, we use big machines that burn oil because there aren't any other kinds of machines that can do that kind of heavy lifting. To refine the ore into useful copper or steel or other minerals, we use natural gas and coal and electricity, often coal-fired and gas-fired, because you can't just take a pound of ore out of the earth and hope it'll conduct electricity. You have to grind it up and get the small percentage of its copper out of there. So that's a long answer to first. If I've told elementary school kids that kind of disquisition, they get it. It's not complicated. I mean, these aren't big numbers. They aren't big concepts. This is how the world operates. That's the real world.
Yeah, I've often found that to get really confused, you have to be an adult.
Or to ask stupid questions, you have to be an adult. Kids ask very good questions. They really do.
Yeah, absolutely. Well, a striking sentence in Mines, Minerals, and Green Energy is this: for everything built or fabricated, one can trace a straight line back upstream to where people use heavy equipment, in some countries just shovels, to extract materials from the earth. Now that points way beyond the iPhone in the hand, the Tesla cruising down the highway, the electricity coming from a wall socket, and the wind turbine blade or the solar panel. All of these derive from physical stuff in the earth. Why isn't that more obvious? And why is it so important? Why is it that so many backers of green energy just don't really think about this at all? Where do those things come from?
Well, I think some people do think about it. It's certainly obvious once you state it, right? I mean, you can't have lithium in a lithium battery unless you dig up lithium carbonate or lithium salt somewhere on Earth and convert them and transport them to a refinery where you can, in a chemical plant, where you can make the lithiated chemistry. And you can't, a Tesla battery, most people don't know, but they can look it up on the magic Google machine again. A battery in an electric car weighs 1,000 pounds. It weighs a half a ton. Uh, one can, without too much difficulty, figure out how many tons of rock you have to dig up to get the pounds of each kind of material, whether it's nickel or magnesium or the cobalt. So I think, the why, you asked the why question, and the why people don't know this, why they ignore it. The why question, I'd like to stipulate, is a question for psychologists, psychiatrists, not physicists. But I have an opinion on the why question. I think why people don't know these things is some cases they're incurious. They just like to believe things they're told, and they're busy. So, or they're curious, but they don't have time, whatever. I think in some cases, people believe things that aren't true. They just really don't do their homework. I think in some cases, they know the facts and they don't care. The fact that children mine cobalt by hand in many of these artisanal mines in Congo. The Congo is a source of more than half of the world's cobalt, which is invisibly refined. By invisibly, I mean nobody pays attention to it. 90% of all the world's cobalt ore is refined in China, where its electric grid is 63% now, I think, coal-fired. So those facts we know. So we have labor practices that have been written about. I mean, some journalists have been very good about this. Wired magazine, even the Washington Post had a feature a couple of years ago about the unethical practices in mining in some African countries for the minerals we need. There's no way in your phone with a cobalt in its battery whether those atoms of cobalt came from a Congolese mine dug up by a child using a shovel and carried to a truck that took it to a Chinese refinery that's in a part of China where they use possibly slave labor. I mean, enforced labor. Right? We know those things are going on. We don't have transparency on those parts of the world. So I think a lot of people practice cognitive dissonance. They just ignore it. They're looking at it, but they just don't see it. And there's a lot of money here. So let me be cynical. The energy business is a big business, and there's trillions of dollars involved, literally trillions of dollars globally, in these energy minerals. And they're in parts of the world where unscrupulous actors can make a lot of money, and scrupulous actors can make a lot of money, both. So, you know, it's one of these sort of ineluctable problems of human nature that we all, of course, we all have biases, right? We want to do well, or say that you want a job, you want to earn some money. It's obvious when you're doing something that's criminal or illegal, it should be. But things that are sort of subtle like this that disappear into the background, it's kind of easier to ignore them because they are subtle in the background. And maybe you don't believe it. If someone like me says it, I try not to read comment sections in stuff that I publish. I publish a lot and there's lots of comments. I almost never read the comments. Once in a while, I get dragged down that rat hole. And, you get accused of being in the, fossil fuel interests, or you're a shill for the fossil fuel industry. Pfft, give me a break. Just look the facts up. I'm a shill for anybody. I'm a shill for reality. But just silly ad hominems happen because people are uncomfortable with the facts.
Yeah, ad hominems, of course, are one form of logical fallacy, and then there are some others as well. Uh, I mean, I've had the same kind of accusations, and I just reply, "Gee, I wish I were supported by ExxonMobil. That'd solve a lot of budget problems."
I take the check. I can tell you they aren't spending any money on PR to support oil. All the oil companies have been emasculated, as have the utilities, for the last 2 decades. They are heads down trying to just do their job because the market demands their product. But except for the trade associations, there's essentially bupkis going on to defend the virtues of producing cheap energy for the world.
Yeah. Well, when I used to actually teach logic in seminary, as a matter of fact, I used to use the question. I used the question, how far is it from 2 o'clock to London Bridge, to illustrate what are called category fallacies.
Well,
In mines, minerals, and green energy, you ask, how much does a mile of travel or a movie weigh? Now,
right.
why aren't those category fallacies? And why did you choose that way to try to get people to think carefully about green energy?
Well, as a master logician, and I am very hesitant to tread under your territory, but the category errors that I was describing are analogizing information machines with energy and materials moving machines. You can use information to move things, but you can't scale physical machines the way you scale information machines. That's a category error. However, it's not a category error to ask questions that seem nonsensical. How much does a mile weigh? How much does an hour of video weigh? Because the question I'm asking there is, how much material is mined each year to make the machines and fuel them? But let's just stick with making the machines, to make the machines that make that service possible. Well, we know the answer to that, right? A car weighs a couple of tons. Okay, well, or a ton, depends on the kind of car you drive. Let's just say 2 tons. So you've got a big car, and you could then say, how many miles do I drive that car over the life of the vehicle? 10 years. Then you can impute a pounds per mile, because when the car is finished, you're going to, quote, throw it away, recycle some of it. But either way, you've had to mine materials that weigh something, and you can then calculate how many pounds per mile of stuff is extracted from the earth to build the vehicle for each mile and fuel the vehicle for each mile. And you can compare that for an electric vehicle, a gasoline-powered vehicle, a bicycle, anything you, a horse. All these things have physicality and they perform a service. And so you just divide the physical piece of it, uh, prorated for the service distance. Same is true for the internet. So this video platform we're on now is made possible by sort of four magisteria of machines. We have to build the machines, the computer itself at both ends of this network, the device that we're all looking at right now. We have to build machines that transport the information, the wired and wireless networks. And then we have to build machines, the data centers that mediate, route, do all those magical things. And then we have to build machines to power it all, because it not only to build it in the first place and to power it while it's running. All those machines are physical. All of them consume materials. We actually know what they all are. You can do research and find out what a router looks like, what it weighs, how much information it can carry. So if we know how many bytes per hour the internet carries, how much machinery is on the internet, what it cost, where it was built, we can then impute a pounds of stuff or dollars of stuff. We generally track dollars because in commerce we care about dollars. Society cares about dollars. But in the environment, we care about pounds. So I started counting pounds. That's why I wrote Mines Minerals. I count the pounds of stuff. So we can then talk about the fact that an hour of zooming entails, 2 pounds of natural gas, 4 pounds of coal, and because it does, the fuels consumed somewhere. And if it was solar powered, well, 400 pounds worth of materials to make a solar array. And how do you figure that out? Well, the solar arrays only last 20 years. They wear out. They have an energy capacity that we can measure. We know how many kilowatt hours they produce on average over a year. So this is all just arithmetic based on common sense. But the point of it is, and the reason I phrased it that way, is to get people focused on the key environmental metric of all time. It's not carbon dioxide. It's not even air pollution. Air pollution is a bad thing. The most difficult thing to manage through all of human history is to minimize our use of the surface of the earth. That's where we live. And we don't live on the water. So the useful, arable, pleasant, occupiable land area, that thin little layer between the subterranean and the atmosphere, is where humanity lives. It'd be nice to use the minimum amount of that and to spoil the minimal amount of that. And that always comes back to the quantity of materials that you need to get to do something, whether it's drive, fly, cook, make food, grow food, go to a movie, whatever it is. It all comes back to a physicality. That's, you could say it's theological. It's because if you're in philosophy, it's not a disputable fact, and nor is it an avoidable fact. But from that derives all the consequences.
Yeah. Excellent. Just want to remind our viewers that we are discussing Mark Mills's study, Mines, Minerals, and Green Energy, a reality check. And the Cornwall Alliance will be delighted to send you a free copy of this as our way of saying thank you when you make a 100% tax deductible donation of any size. Doesn't matter how large or how small. When you go to cornwallalliance.org, just click on the donate button, and as you fill out the donation form, when you come when you come to the comments field, just put in there promo code 21-04 and the word mines, and we'll know what you're asking for. So please consider how you might be able to help the Cornwall Alliance to continue our work of education around the world. Have a couple of quick comments that have been written in on our Facebook page. I'd like to just quickly pull those up, and Mark, ask you if you would just give quick responses to them. One viewer wrote that she had she had read that lakes in China became toxic dumps from mining rare earth minerals for technologies. Can you comment just a bit on the magnitude of that problem, and why is that happening there when it's not happening, or at least not nearly at such a scale, in democratic countries?
Well, as the viewer probably knows, China is the source of about two-thirds of the world's rare earths and about 90% of the world's rare earth refining. Refining rare earths is difficult. These rare earths aren't rare. Let's just clear up something for people. They have rare properties. So neodymium makes magnets incredibly powerful. Dysprosium makes them very temperature resistant. So they're rare properties, but they're common. They're about 1,000 times more common than gold. So
Hmm.
America used to provide about two-thirds of the world's rare earths 40 years ago. We now provide nearly zero, not quite zero. We made the decision essentially not to expand mining and even to contract mining in America. In non-democratic, non-transparent societies, they can mine cheaper than we because they don't have our environmental rules. So the viewer is correct. We do know something about environmental problems in China from their mining practices. And we do know that they're trying to clean up as they become wealthier, which is a normal trajectory for societies. But we also know that they're not particularly honest with us about what's going on. It's a little hard to see. See some of them from satellites. So. But the viewer is exactly correct, and there are rare earth elements of all magic technologies. You know, uh, these are essential elements in everything from lasers and smartphones to electric cars and military products. And we make a lot of things that you can't make but for the rare properties of the rare earth elements.
Yeah. Okay. So Vicky Zaccarda, thank you for that comment. We have another one here from Guy Takamatsu. And Guy says, Mark Mills says something similar to John Couch about the green appeal to non-existent technology, which we haven't even invented yet.
Yes.
Says, if you believe that reducing emissions is the solution to global warming, as Couch does, then you would
Mm-hmm.
go nuclear, not wind or solar, which are
Correct.
used with dirty brown coal. And Couch is even angry with those green advocates and points out the technical and cost problems of wind and solar in his video, Solar Wind Incompetence. You want to just quickly relate to that? What is John Couch saying, and how would you compare your thoughts with his?
Well, he's joined by other people like Michael Schellenberger in his excellent new book, for those who haven't read it, on the apocalypse not. Um, Michael believes climate change is an important issue to deal with, and he's furious, properly so, at the myths and silly things said about wind, solar, and batteries. Not that they're not useful; it's that they can't solve the problem they claim to be solving. Uh,
Yeah.
Even more, Michael Moore's movie Planet of the Humans, which I love the title, I have to say, although he means it differently than I mean it. Yeah, he's furious about the lies, what he calls lies, and the kleptocracy in the green orthodoxy about the environmental damage caused by the kinds of things that are being pursued, and that they aren't solutions. So there's a community of environmentalists with whom I don't agree about a bunch of things, but we agree about a lot of things, particularly about this being not a way to reduce carbon dioxide emissions if that's your goal, or a way to improve the environment. Nuclear energy is the only magical, well, it's one of the two only magical phenomenologies that mankind has ever concocted in thousands of years. The other is the photoelectric effect for solar cells. The advantage to nuclear, because they're both kind of atomic phenomena, the advantage to nuclear is its density. They're both phenomenologies that are different than moving things and spinning things, and uh, there's nothing comes close to the energy density and therefore the minimizing of humans' footprint to nuclear. Turns out nuclear energy, to make it cheap and reliable and widely deployable, is harder than we thought. But I'm extremely optimistic about the next generation reactor designs. That's where money should be going. And that will profoundly alter the equation with respect to the electric sector. It won't solve the issues in the 80% of the world's energy economy that's not electrified. And even if you increase the electrification of transportation and steel making and heating, which you could double that. Let's say you go from 20% of the world's energy as electric form to half. You're still left with half the world's energy has to come from something. And it'll almost certainly be hydrocarbons, almost certainly for the next century or longer.
Okay, now we normally go right about an hour on this program. We are now coming up on 56 minutes so far, and we're about halfway through what we've planned. So I have to ask you, can you stay with us for a while longer? Maybe not another entire hour, but another 20 minutes, half an hour?
Sure. Let's see if we can stretch the tolerance of our internet-enabled audience.
Yeah,
Keeping in mind that
how
we're
much?
consuming photons, bits, and the hidden energy keeping us lit up here is not trivial.
Right, yeah. How much does an extra half hour of From the Stacks weigh, we might ask. So
We
let's get
actually
some
know.
hard facts up. Pardon?
So we actually know. We actually have a good idea what those numbers are. An hour of
Yeah.
video allocated for each person watching, their personal energy use for the internet for video is roughly equal to their energy allocation for going about 5 miles in a bus. So it's not bad. It's pretty efficient, but it's real energy.
Okay, all right. So, in a sidebar in your study, you point out that we have to extract about 500,000 pounds of earth before we can even begin the construction process for a 1,000-pound electric vehicle battery. That's 500 times as much material as actually goes into the battery. What are the components of that, and why is this so important to questions of the environmental impact of so-called green energy?
Well, this takes me back to my earlier career. One thing that's not in your overlong introductory bio is that I worked for a Canadian uranium mining and refining company early in my life. I've been at the bottom of I think it was a 7,000-foot vertical hard rock shaft in the Arctic Circle. So I kind of like mines, and I like mining, and I've been around miners and geologists a bunch of my life. So this is let's use nickel maybe and copper rather than the unusual elements, because you're going to use a lot more nickel in batteries. You can avoid copper by using nickel, and it's a very reactive metal, and it's what Elon Musk is pursuing right now, and use copper for all the electrical system. But you know, a copper ore, rocks that contain a significant percentage of copper, it's called ore. They contain about 0.5%, 0.2% of the rocks, the ore's weight is in copper. So, or put differently, if it's 0.1%, which is not uncommon in some low-grade copper mines, that you can do the math. It means that if you want a pound of copper, you're gonna be mining 1,000 pounds of rock. You have to dig up 1,000 pounds of ore, but you also have to dig up probably 5 to 10,000 pounds of other rock that's in the way to get to the ore. Then you dig up the ore, the 1,000 pounds, and then you get the pound of copper. That reality is locked into how elements are distributed. Some elements are much more densely common in the ore, and those are therefore far more valuable to a miner. You have to dig up less stuff. Gold is rare, as people know. That's why gold is expensive. It costs something on the order of $300 to $500 worth of fuel, diesel fuel, per ounce of gold mined. So if the price of gold goes down too low, which is not going to, it goes below the cost to mine it, you don't mine it, right? I mean, you've got to sell it for more than the cost of the fuel and the machines and labor. So batteries are just big boxes full of thousands of components. Let's frame the 1,000 pounds for people, because they're thinking the electric car is simple. We're making a simple swap. It's much simpler than an internal combustion engine, we're told. That's not true. That's, again, this is just a failure to be curious. It's true that an electric motor has 2 moving parts compared to an internal combustion engine, which has hundreds of moving parts, sometimes 1,000 moving parts, depends on the engine. So we switch out the internal combustion engine, a lot of moving parts, for an electric motor with 2. The fuel system on an internal combustion engine vehicle has an electric pump with two moving parts and a tank. Moves liquid. A battery weighs 1,000 pounds. Your fuel tank, when it's full, weighs about 100 pounds. So the battery weighs 1,000 pounds, and it contains thousands of parts, about 10,000 welds, cooling system. It contains power electronics. It contains separators. It contains anodes and cathodes. It contains a lot of stuff. It's a complicated electrochemical machine made from a lot of components that are welded and assembled and packaged together. And it wears out. And it wears out the same way that an internal combustion engine wears out. Internal combustion engines wear out sort of at the molecular level. That's wear and tear. It's a mechanical molecular wear out. Batteries wear out electrochemically at the molecular level. They become garbage after a while. They just wear out. So you've just swapped the complexities, but an internal combustion engine weighs a couple hundred pounds. Some weigh less, some weigh a little more. The battery pack weighs, again, 1,000 pounds. So the swap's not so good. I mean, the electricity that you put in the battery doesn't really weigh anything to speak of. Essentially, it weighs nothing because you're just moving around ions. You're not adding net weight. So you have this sort of mythological trope that there's complexity in one and not in the other, the complexity in both. In fact, the internal combustion engine is mostly steel, which is very easy to recycle and very inexpensive. It happens to be made from elements that are very common in the earth. Iron. Iron is one of the most common elements in Earth's crust. So getting the iron to make steel for an internal combustion engine involves a lot less mining per pound than getting the nickel and the copper, the cobalt and the magnesium and the other elements to make a battery and a battery pack. So that tells you a lot about what the challenge is. It also tells you something about where you get the stuff. I mean, we produce essentially all of the oil and gas we need in America. We export gas. We're net exporter of gas. We're almost a net exporter of oil. We used to be, our oil products. But on all the other energy minerals, we're a net importer. So going to batteries not only increases the quantity of materials, it means we're swapping sources. We're going from liquids and gases that we produce domestically to solids that we import. And the quantities are significant and the dollars are significant. We're swapping out a roughly $300 billion a year domestic industry for $400 to $500 billion a year worth of imports. Roughly a swap negative to the economy that approaches $1 trillion a year. This would be I'm speaking in terms of if you swapped out all of the oil and gas used in America for batteries and wind and solar and stuff. It would be a profoundly negative economic swap at the macroeconomic level for the American economy.
Yeah. Now you present comparable data in terms of the pounds of stuff necessary to make batteries. You present similar information regarding the making of wind turbine blades and solar panels and various things like that. But hey, you have to dig up stuff to make internal combustion engines and gas-fired generating plants and coal plants and hydro dams and nuclear plants and so on. How does that compare? What's the, how would you compare the how many pounds does 100 gigawatts of electricity generated by wind or solar weigh versus how many pounds does a gigawatt of electricity generated by gas or nuclear or coal weigh?
Yeah. Well, the short answer is the tons per unit of energy delivered, whether it's gigawatt hour or kilowatt hour, but the pounds or tons per unit of energy delivered goes up at least tenfold when you build wind, solar, or hydro machines compared to coal or gas or oil machines. So there's a tenfold increase in the quantity of materials mined to make the machine. That's not counting the specific minerals, that is the rare minerals that you need to make motors and magnets. If I go to that sort of, not by talking about the tenfold increases are things like concrete, glass, and steel. The big quantities you need, the big elements. Then when you look at the things like dysprosium and neodymium and seleniums and lithium and cobalt, that set of elements, those class of energy minerals, you need not 10 times more, you need about 50 times more per unit of energy delivered. Use less of the material, but you need 50 times more of it than in a generator set for a gas turbine or an oil turbine. So the numbers are big. It's huge. It doesn't mean you can't do it. And glass is cheap. You can make lots of glass inexpensively. The problem is on the other side of the equation is that when the machines wear out, which is where we started talking about those stuff, you have a lot of stuff to dispose of. You have 10 times more stuff to dispose of in tons. And some of the stuff is tough to dispose of. So if you think maybe in more specific terms, if I had a typical 100 megawatt gas turbine, which is about size of a residential house, that's how big the turbine is, physical, but that can power 75,000 homes. So call it 100,000 and 150,000 people. I can replace the gas turbine with wind turbines. I need about 20 of them, not one. Each is the size of the Washington Monument, and they have to be spaced out on 10 square miles. And each of those turbines has a 45-ton blade made out of non-recyclable fiberglass. Each of those turbines. So when the turbine is finished, that one turbine, it has 45 tons of non-recyclable plastic. One turbine, 20 of them to replace that one gas turbine. That one wind farm, it's a tiny wind farm we're talking about, remember, for 75,000 homes, will lead to the need to dispose of more non-recyclable plastic for, again, that one 20 turbine wind farm than all of the world's plastic straws combined. So it's the scales are they're just big. Is that am I worried about it? I'm personally not worried about it. I don't think either of them are particularly a big worry. But when people talk about the environment and they worry about it, and they, we got all this twist in our knickers, so to speak, about plastic straws. Please, come on. I mean, the first that are recyclable, and it's bad when a lot of those plastic waste is coming out of the Chinese rivers, Yangtze in particular, not from our country. These are small problems compared to the scale of the material problems we're going to generate with the quantities of materials that will have to be disposed of when wind farms and solar arrays and batteries wear out. There's just lots of it.
Yeah. Yeah, you put a chart into your paper, Mines, Minerals, and Green Energy, that I think is really, really helpful just to visualize the scale of difference, or rather the difference in scale of the amount of stuff, the materials requirements to build different energy machines. Folks, now we've got that up on the screen now. You can see for natural gas, it's what, about maybe a 15th of what it is for
Right.
solar PV.
Right.
Hydro's pretty far up there, but wind is pretty far up there too. And hydro also, I understand, typical hydro dam can operate for 100 years or more, whereas a typical wind turbine, you might get 20, 25 years effective life out of it. Solar PV has an
Right.
even shorter effective life. Geothermal is much more material intensive than natural gas, and coal, oil, they're kind of similar to natural gas on that. And again, it
Exactly.
comes back to the fact that they are so energy dense as we find them in nature, as distinct from solar and wind, and even comparatively hydro, which are energy diffuse as we find
Correct.
it in
Right.
nature. So, in order to convert that very diffuse stuff into highly concentrated stuff, we just simply have to have a lot of space, a lot of material,
Right.
and a lot of work. So
Well, it's also a lot of land. I mean, back to the point that land is precious. There are some environmental organizations and a lot of citizens are it doesn't get a lot of news coverage, but one can find the stories objecting not just to big hydro dams flooding large areas of land, but to massive wind farms occupying large areas
yeah,
of land, because I like how they look personally. I think they're magnificent engineering achievements. I don't like when they're on countryside ridge lines that I thought was beautiful before, but I'm not offended by them personally. I've been in wind farms that go to the horizon, in China. They're amazing. But not everybody agrees. Certainly, in terms of environmental impact, they have real environmental impacts, and I'll say one of the obvious ones that was in the news and then just dropped out of the news. But wind farms have got themselves exceptions for Endangered Species Act killing of birds like bald eagles that you never would see provided for conventional energy sources. It,
Yeah.
it's a form of hypocrisy that it really sort of rankles people, and it should.
I think we finally found something on which we would disagree, and that is the aesthetics of big field of wind turbines.
Well, I'm
I
stipulating it depends where
remember,
they are. It depends where they are.
yeah,
I just said if it was on the landscape, like if it was in my view, looking from my summer home, I don't want to see them. I'm just kidding.
right, NIMBY, right? Not in my backyard.
No,
I
look,
remember
the truth, the reason
about,
the Twilight of Fuel subtitle, back to where we started, the purpose of that title is not just the economic twilight. You want energy sources to not occupy the visual landscape, to consume land,
right,
to not just to spoil it. So no one liked coal mines back in the day when they didn't reclaim the land. Well, for good reason. We should have reclamation. But no one is talking
right,
about the reclamation challenge with wind and solar. And it will be epic because the quantities are huge.
yeah. Yeah, Vicky Zaccardo just put another comment up saying, wind farms are big industrial complexes of concrete, steel, oil, etc. And that leads right into a comment that I wanted to make here, and that is, I won't call them wind farms. I call them wind factories. On a
Well,
farm you grow
yeah,
wheat and corn and rice and things like that,
yeah,
and cattle and chickens and so on.
yeah.
These are factories, plain and
Right,
simple. They're not farms.
right.
I remember about 2015, I think it was, so about 6 years ago, I was driving Interstate 10 from Phoenix to Los Angeles.
I know the
Hadn't
one.
been on that route for about 25 years or so. And I used to drive that route actually 4 times a day when I was a truck driver back there shortly after college. And there's a point where coming westbound on I-10, and you come into the valley between Mount Sagonio on the right, the north, and Mount San Jacinto on the left, the south. And there are these two snow-capped mountains, snow-capped usually all the way into the middle of summer, with this desert valley between them. And it was just beautiful. And as I topped a rise in 2015 and saw down into this valley for the first time, the whole valley was filled with turbines.
Yeah,
And
I know.
I confess, I simultaneously shed some tears and shed some expletives. I was so
Yeah.
ticked.
Well, but
And
think
it just amazes me that people who call themselves environmentalists
right.
have so little qualm about the aesthetic impact
Well,
of
this
wind
remember
factories.
the environmental movement began, as you well know, largely with Teddy Roosevelt and preservation of nature's beauty. And
Yeah,
you say it exactly correctly. The goal is to build a machine, a factory that can produce energy continuously for society because we need it continuously. You want that machine to be as small as possible, ideally invisible. So compare what you just described, square miles going to the horizon of machines on the surface that are a factory to produce synthetic electricity. It's essentially what we're doing. We're not making natural electricity, we're synthesizing it out of these giant machines, this factory. Compare that to a single, that whole horizon you looked at could be replaced by a single oil well on a pad 100 meters by 100 meters with nothing else visible, with the entire factory below the surface, 7,000 or 10,000 feet down, producing energy that's in pipes below the surface, going to a single turbine in a building the size of a barn. And that's it. The entire horizon that you saw filled with hundreds of wind turbines on the surface could be replaced by two things that one of them I could make look like a barn, and that's been done, by the way. Bechtel makes gas turbine power plants look like barns, fake barn covering, and the total factory, the shale oil and shale gas revolution, is a manufacturing revolution. We are manufacturing oil and gas out of shale rock that happens to house what's called the source rock for oil and gas. We manufacture liquid oil and gaseous natural gas from
Yeah.
rocks in a factory that's almost entirely below the ground. It's only visible briefly when we drill the wells and bring the equipment in to do the drilling, and then it all goes away after 3 weeks. It's talk about a gift to the environment in terms of the profound visual reduction. But yeah, I agree with you. It's a shocking abrogation of responsibility for preservation of nature's beauty.
Yeah. Right. Well, for decades, though, people have trumpeted the message that in our increasingly service and technology oriented society, we are dematerializing. What does that mean, and how realistic is it? And you might make reference to another chart in your paper called Global Use of Materials to
Yeah,
help,
no,
our viewers grasp the scale of this stuff.
I, I, the dematerializing trope is really an interesting one. So I'm sympathetic to it because, again, definitions matter. So if I said we're dematerializing, you'd think we're using fewer materials on the planet. This graph you just put up is UN data. Data is available from OECD. This is all the materials the society uses each year measured in tons. In fact, measured in billions of tons, gigatons. From the period, I think I have 19, what did I do, 75? Yeah, the oil
Yeah.
embargo periods. Last 40, 50 years, half century kind of period. So the world has gone from using 20 to 100 gigatons of materials a year. I mean, we're not dematerializing. These are, the biomass is food and wood. Obviously, construction materials are concrete and stone and all this, and then oil, gas, and coal, obviously, and metals. That's everything. Humanity extracts from the earth and moves around. Gigatons of it each year. I mean, it's millions of pounds per person extracted from the earth for a year to support humanity and civilization. So how would you say we're dematerializing? Well, if I put on the same graph the wealth of the world, as you know,
Mhm.
it's grown far faster because of technology and the servicification of everything and the digitalization of everything. We're getting wealthier, not wealthy enough for enough people, but overall the world is far wealthier. So the amount of material use per dollar has collapsed. No doubt about that. We use far less material per dollar of economy. So if you say we're dematerializing in the economic sense, yes, but that's the subtitle of our book back in 2005. That's the twilight of materials. That's what you want. But the economy and the services that people want grow faster than that efficiency. Hence, you get this curve where you have the net absolute quantity of materials goes up. This only peaks, only stops when we finally have all of humanity living with the comforts and the safety that everybody would like, because all the comforts and safety, beauty, travel, leisure, all come with using more of this stuff for more people.
Yeah. Um, what about reusing and recycling energy producing machines? Can you give us some sort of a general comparison between uh, how much you can reuse and recycle the kinds of things that go into so-called green energy versus how much you can reuse and recycle the things that go into, internal combustion engines, coal-fired power plants,
Right.
gas-fired nuclear plants, things like that.
Well, we've spent what 4 or 5 decades now on the recycling mandates and belief that we should recycle stuff. Humanity has recycled useful things for all of history. This, if something's valuable, you reuse it. The measure of value is how much it costs you to recycle it versus how much it costs you to get a new thing. So I mean, it's that simple, right? So you could say you have to recycle anyway, even if it costs more. That's a political, social question. But the physics and engineering question is, does it cost more to recycle it than to get the virgin material? So a few things are pretty easy to recycle. We've gotten very good at it, inexpensive: steel, lead, um, and aluminum. Everything else is pretty hard, and a lot of stuff can never be recycled. The consumables, food and biomass, are not, and energy, and you can't recycle oil when you burn it. I mean, these are just, they're gone, right? But on the material side, overall, society recycles less than 10% of what we produce each year. So the goal is to get up to higher levels of recycling economically. Here's the essence of the problem. Let's use neodymium as an example. It's a rare earth element that's critical in the magnets and wind turbines. So if we could recycle it, we could have to mine less of it and buy less of it from China. Well, there's two problems with recycling. One is, if you recycle, whether it's significant or not, in terms of the demand for mining, depends how fast your growth in the material is. That put differently, if the growth and demand for neodymium to make new magnets for wind turbines is 100 times greater than the quantity of material I can recycle in a given year, the recycling is in the noise. It doesn't change the fact I have to mine more. That's where we are with most stuff, where growth rates and demand outgrow the quantity of stuff available to be recycled each year, even if you could recycle it all. It's not true for everything. It's true for most stuff. The more important issue is, if you need more neodymium, the question you ask as an engineer or an economist is, how much does it cost me to get it? That's the first order question. And in dollars, then you ask it in environmental terms. The cost to get it is determined by its concentration. Just like, does the ore contain 2% neodymium, 0.2%, or 20%? Obviously, it determines the cost. Well, it turns out that the concentration of neodymium in waste stuff is lower than the concentration of neodymium in new ore. So there's more available per ton in the ore in nature than there is in the garbage from human nature. And nature has its stuff in a sort of homogeneous form. It's a rock. When I break the rock up, there's some stuff around it, but not much. Recycling smartphones, for example, contains all kinds of stuff. It's messy, dirty, complicated. It's the worst kind of ore you can imagine, and therefore far more expensive to re-extract an ounce of silver out of a smartphone than get it out of the ground in the first place. Does that mean you shouldn't recycle? No, I mean, there's actually a lot of good cases where recycling isn't that much more expensive. Should do it, I guess. In some cases, you should definitely do it, especially if the thing you're going to throw away is damaging to the environment. Don't throw it. We don't throw lead away because you don't want lead in the water stream, right? You just don't want it to contaminate things. You want to capture it. So we recycle it for health reasons.
Yeah. A bit ago, you made some reference to what happens to wind turbine blades, and you have I think, a stunning graph in your paper on the annual production of waste from global wind turbine blades. We'll show that one up here, and just kind of draw the lesson from this for us, will you?
Well, if viewers can't see it, it's we're talking millions of tons a year of waste, non-recyclable plastic from wind turbines. Why is it non-recyclable? One might ask. It's because they're made out of fiber, not carbon fiber, but it can be carbon fiber. They're made out of fiberglass composites that are extraordinarily difficult to recycle because you have to make them extraordinarily strong and light. So they're sort of incommensurate goals. This is not, I should point out, the graphs you're showing and all the graphs in my report aren't stuff that I've made up. It's not like I'm making this stuff up. These are typically from OECD reports, from United Nations reports, from what's called IRENA, the International Renewable Energy something agency. I forgot. I apologize. So these are all data that are available to everybody, including environmentalists. In fact, a lot of environmental organizations are the ones publishing this data. They're worried that as the world rushes to building more wind turbines and solar arrays, I could have put a similar graph. It would look just like this, with numbers that are 150% higher for waste glass and from solar factories, to use your phrase, rather than solar farms. There's a lot of glass that has to be disposed of. The glass contains metals to give the glass photo stability. Those metals make the glass not recyclable, at least not at a cost anybody will pay, and also hazardous waste. So this is not hazardous, it's just not recyclable. The solar glass that has to be disposed of is hazardous waste and is similar, and as I said, greater quantities coming. So what do you do about this? Well, you dig holes and put it in the ground. I mean, that's what will happen. That's what's happening right now, because there are thousands and thousands of wind turbines reaching their end of life now, because they last about 20 years. We've had them around for 20 years. We're starting to see decommissioning happen. Throw the blades out, but they typically leave the steel tower and the concrete pad there. Question I guess I'd have is who's what you saw cresting that hill at the valley full of wind machines, when they're all worn out, who's going to decommission it? Whose budget is that in? Well, the answer ultimately is taxpayers. But right now, the people who build the wind farms, so far as I know, there's nowhere in the world that they're being required to set aside money to decommission and reclaim the land to look like it used to look before the giant wind factory was built.
That is truly amazing. I mean, to think that we would have construction permits for something that we know is going to go obsolete in, say, 20 years, and there's nothing in that permit that requires the decommissioning, the removal, the restoration. I mean, a lot of folks get upset about the fact that so much surface coal mining used to be done without any land reclamation.
Now
Now,
it's
pretty much
required.
all of it is
Yeah.
reclamation, frankly, there are places where there have been tremendous strip mines, and you would never know it. They're just beautiful now. They're
Right.
beautifully
Right.
reclaimed. Anything from golf courses to forests.
Right.
But we don't put the same requirement on wind turbines or solar arrays. Well,
Well, we
let's
also don't put that requirement into the mines where the materials come from overseas.
yeah, right. So you spend several pages, Mark, talking about the geopolitical consequences of the fact that what was it, 90% of the refining of rare earths takes place in China. And I think it was, I've forgotten the percentage you said of the actual quantity of rare earths that come from China, and then a good deal as well from the Democratic Republic of the Congo, which I suppose Congo is true about that name, but not Democratic or Republic. But you know, why? What are those? What are those geopolitical problems, and where do you see those going over the next, say, decade, perhaps?
Well, we could start with the facts that are unavoidable. I mean, we're going to build a lot more wind turbines and solar arrays, and we should build a lot more, by the way. We shouldn't just spoil countrysides, but there are places where they're very useful, and countries where they're very useful, locations. It depends on where you are on the surface of the earth. But what won't happen is the world won't stop using oil anytime in the foreseeable future. Say many, many, many decades, I think centuries, but in the time frames where geopolitics matter, let's talk about the next decade. There is no scenario from any credible organization, the International Energy Agency, UN, anybody, which doesn't see the world using 10 years from now about as much oil as it uses today. In other words, the most optimistic scenarios will see the oil use drop 10 or 15%, which would be a lot, by the way, if that were to happen, and gas use and coal use similarly. But that would still leave the quantities of oil and gas, coal the world needs, essentially at the levels they were, say, 20 years ago. Huge, in other words. So the world is going to need lots of hydrocarbons for the geopolitically usefully foreseeable future. So the interesting geopolitical question is, who provides it, right? If we know where most of the world's, let's stick with oil. We know that the majority of the world's oil comes from three places: the United States, OPEC, and Russia. That's it. It's the majority of the world's oil. It's not all the world's oil, but it's a majority. We know that the 5 regions of the world that comprise 75% of the world's GDP, of those 5 regions, one is the United States. Of those 4 regions that are not the United States, all of them, including China, India, Japan, Europe, are have increased and are increasing their dependence on imports for oil, gas, and coal. All of them. Rapidly increasing, not a little bit. Even with renewable programs and electric cars, whatever, biofuels, whatever you want to invoke, they're all increasing their dependence on imports for oil and gas and coal. Right now, have for the last two or three decades, or will continue for 2 more decades. The United States was the only major economic region in the world where we're not only not increasing our dependence on imports, we actually became an exporter of net exporter of natural gas, and we're on track. We were on track to becoming a net exporter of oil. This is a stark difference. The world needs those fuels. Countries, economies can't function. China cannot function without oil, gas, and coal. It's not going to function. It can't operate. No country can operate without oil, gas. It is in fact existential threat to an economy, any economy in the world, if they lost their access to oil, gas, and coal, because 80% of the world's energy comes from oil, gas, and coal. Most of the rest comes from not wind and solar. They combined provide less than 2.5% of the world's energy. And even if we have a tenfold increase in those, they won't get more than 15% of the world's energy. So we got oil, gas, and coal are providing these incredibly critical economic and social supports of all these economies, these major economies. Some of them are not friendly to us. Some of them are friendly to us. The geopolitics of where that comes from are obviously critical. So what do you do if you're China? They're now the largest importer of coal in the world, the largest importer of natural gas in the world, the largest importer of oil in the world. We're the largest producer of natural gas in the world, largest producer of oil in the world, and we were on track to become one of the biggest exporters of natural gas, probably will be. And we were on track to, as I said, become a net exporter of oil. We don't need to import oil. We could choose to import oil by policies, but we don't need to. So what does that mean geopolitically? Well, if you're China, you need a bargaining card. So, and I'm not trying to be cynical or Machiavellian. If you need a bargaining card, what's a good bargaining card? Well, rare earth minerals, refining cobalt, refining the minerals that are critical to all machines, modern machines, computers, telecommunications, weapons machines, is a great bargaining card. So China now mines 90% of the rare earths in the world, refines comparable percentage. That's a very nice bargaining card. What would you do if you were at a negotiating table and the implicit, not explicit dynamic is, and it's been, this is not, I'm not spinning hypotheticals here because it's already happened, is that if we behave in a way that is antithetical to China's interest in increasing its purchases of oil from Iran, which it just did, it struck a multi-year deal, hundreds of billions, I think it might have been a $500 billion deal over a decade to buy Iranian oil. We're not particularly friendly with Iran and vice versa, but China likes their oil as a hedge against other people's oil. Were we to interfere with that in some fashion, they have a bargaining card. They could interfere in some fashion with our access to rare earth minerals. And by the way, apologies for the dog bark, the hazards of Zooming. So anyway, I'll stop there. The dog interrupted me.
Yeah. So what would it take? I mean, to do a Manhattan Project or a moonshot to make the United States to make the United States independent in terms of rare earths? I mean, as you mentioned, we've done very little mining in this country over the last couple of decades, 3 decades, I guess. How long would it take for us to be able to replace that, where China just wouldn't have that bargaining card anymore?
Well, first, we do a lot of mining still. We just didn't increase our mining commensurate with our economy. So our mining has slightly shrunk in absolute terms, but in relative terms, we've lost certain specific kinds of mining, like rare earths. But for like iron ore and nickel and copper, we do a lot of mining. Talk to the senators from Arizona about that. It's a big mining state. But the answer is obvious. We should be friendly to mining again. We know how to mine in environmentally sensible ways. We have all the resources. One of the richest geophysical provinces for all these minerals, including rare earths, is North America. We have the capacity, we have the technology, we can do it in responsible ways, but we have a environmental policies that are hostile to mining. It takes decades to permit a mine in the United States, decades. So what's the solution? Decide we care about mining, and don't abandon environmental regulations, but for goodness sake, I mean, Australia and Canada can open a mine up in 4 or 5 years. We have to take 20 or 30, and they'll open up a mine in half a year in Africa by ignoring any kind of environmental regulations. That's what we're competing with, and we're not being serious about it.
Okay, well, this has been fascinating. I'd like to just bring us
And
to
my,
a close by.
and my dog is losing its patience, apparently. I apologize.
All right. Well, what are you working on now, Mark? What can we look forward to as your next contribution to our understanding of the science, the engineering, the economics, the politics of energy that's so crucial to lifting and keeping people out of poverty?
My near-term project is a revisit of the state of the shale oil industry and gas industry in America, because it's a critical one. It's the single biggest energy revolution in a century. Most people don't appreciate the fact that from 2007 to 2017, a 10-year period, the increase in energy production from America was the biggest increase in energy production the world has ever seen at any time from any source. Full stop. Amazing. Can that happen again? I think so. I'm going to write about that. My next Manhattan Institute paper. I'm writing an article, which should come out shortly, about the question, do we know for a fact that electric cars reduce carbon dioxide emissions? I mean, if that's the reason we're pursuing them, which we're told, do we know for a fact they do? Spoiler alert, we don't know for a fact that they reduce carbon dioxide emissions. They can, but not necessarily, especially at the scales we're talking about. And the third big project I'm working on, I'm on the tail end of the editing for my next book, which my publisher tells me will come out in October. I hope that happens. The book is only about energy in a few of the chapters. 3 of the 30 chapters about energy, but energy is infused throughout the book. The book's title is The Roaring 2020s. The subtitle in this particular case is a little different than the last one. It's How the Cloud Kicks Off the Biggest Economic Boom in History.
Hmm. Well, I look forward to all of those new ventures, and just have really appreciated everything that I've read by you in the past, and it's been an honor and a privilege for me to just get to talk with you directly here, Mark. Thank you so much for coming on. Do you have any
Thank you
closing
for.
comments?
Well, I just thank you for all the time. My apologies again for a dog that has less patience than maybe a lot of your viewers. Maybe your viewers feel the same way. They're ready to start whining. I guess I would close by, I feel often when I talk about the physics challenges in Green Dreams, and people think that I'm a naysayer who can't get stuff done, when in fact I'm a profound optimist about what engineers can do. And I like what engineers can accomplish, but I'm offended by true myopia and decisions that I think are fundamentally immoral that cause more harm than good. Those are the things that why I do this, so the reality checks. Not because we won't have more electric cars or shouldn't. Of course we should. Electric cars there'll be tens of millions, hundreds of millions of electric cars in the future. Of course there will, but they won't replace oil. I mean, that's the reality check. That's sort of, it's almost infantile. It's like a tantrum from a second grader saying, I want this something that they can't have. So I sort of want to end on that note, because I'm not a nego, as they say. I really am profoundly optimistic about actually people understanding these truths, and we'll say reality prevailing ultimately.
So we might call you the optimistic curmudgeon, I suppose.
I don't think of myself as an optimist or a pessimist. I think of myself as a realist. But in our world, being a realist, depending on where you're from politically, is either one or the other two.
Yeah, right. I think so. Well, Mark, thanks again so very much for joining us tonight. And all of you out there who have been watching and who will watch later as you come to these programs, thanks very much for doing that. I want to just remind you that throughout the month of April, as our way of saying thank you, when you make a donation of literally any size to the Cornwall Alliance and ask for it, we will be glad to send Mark Mills's wonderful study, Mines, Minerals, and Green Energy, a Reality Check. To request your copy, just go to cornwallalliance.org, and in the comments field of donation form, write in promo code 21-04, or just simply the word mines, and we'll be glad to send this to you. Next week, our guest will be Ben Lieberman of the Competitive Enterprise Institute, and he will be discussing with us how California's energy policy harms the poor in that state. So I hope to see you then. And meanwhile, God be with you, and take care.